Welcome to Instranexus Masterclass on the Master Document Deliverable List for Instrumentation and Control projects. Whether you are a junior engineer or a project manager, understanding the flow of documentation is critical for success. We are going to break this down into the three major phases of a project. The first phase of our journey is Phase 1, Conceptual Design, or the Feasibility Study. At this stage, we aren't building the plant yet. We are defining what it could look like. The primary deliverable here is the high-level control philosophy. This is a brief document that outlines the basic strategy for control and safeguarding. Next, we look at the preliminary system architecture. This is typically a simple block diagram that shows the major control systems, like the BPCS or SIS, and how they might interface with potential packages. We also generate a technology selection report to assess suitable vendors and technologies. Finally, to determine if the project is viable, we produce a rough instrument count based on preliminary lists and a budgetary cost estimate, usually accurate to within plus or minus 30 to 50%. Now we move into Phase 2, Front-End Engineering Design, or FEED. This is where the project begins to take real shape. The vague ideas from the concept phase become the definitive control and shutdown philosophies. These are fully developed versions of your core documents. The most critical document here is the Basis for Design, C&I. This is the foundational document that details all the codes, standards, and specific client requirements that will govern the rest of the project. At this stage, we also create a draft instrument index and I/O list, providing a preliminary but comprehensive list of signals. We also refine the preliminary system architecture into a detailed diagram showing controllers, servers, and network topology. This phase sets the rules for everything that follows. Continuing with the feed phase, we must also address the physical and logical strategies of the plant. We generate critical instrument data sheets. These are specifically for long lead items, like complex control valves or analyzers, that need to be ordered early. We also begin drafting the preliminary cause and effect diagrams, which outline the primary shutdown logic. Another major deliverable is the package interface strategy, which defines how the instrumentation interacts with major vendor packages. On the physical design side, we produce the control room concept layout to visualize the operator environment, and the main cable routing concept, which shows the high-level paths for your main cable trays and trunks. These documents ensure that when we hit detailed design, we aren't guessing about space or logic. We have now arrived at Phase 3, Detailed Design, often called EPC. This is the heavy lifting. First, we finalize the core design basis and philosophies. This includes the final issue of the design basis and the control philosophy for implementation. Crucially, we issue the shutdown philosophy, ESD, and the fire and gas philosophy. We also produce the control narrative, which is a detailed, unit-by-unit description of exactly how the plant is monitored and controlled. Finally, we have the alarm philosophy. This is vital for operator safety, as it defines alarm management, prioritization, and rationalization according to standards like ISA 18.2 or IEC 62682. These documents are the rulebook for the programming team. In detailed design, data is king. We manage this through key lists, schedules, and indices. These are often live databases tracking every component. The master document is the instrument index. It lists every single tagged instrument, its service, location, and P&ID reference. Next is the I/O list. This details every signal, whether it's 4 to 20 mA, digital output, or Modbus, and maps it to the specific system cabinet and channel. We also have the cable schedule, which tracks every cable's origin, destination, and routing, and the junction box schedule, which lists all JBs and their associated instruments. Finally, the alarm and trip setpoint list formalizes the specific values and priorities for every alarm in the system. Now we look at the brains of the operation, the system and network design. We start with the system architecture for the BPCS, SIS, and F&G systems. This is a high-level diagram of your servers, controllers, and workstations. This is supported by the network architecture diagram, which details protocols like Ethernet IP, VLANs, firewalls, and cybersecurity measures. To tell the programmers what to build, we issue the Functional Design Specification, FDS, which translates the control narrative into specific logic requirements. We also define the look of the screens via the HMI Graphics Design Specification. Physically, we produce system cabinet layout drawings and power and earthing philosophies to ensure the systems are powered and grounded correctly. Design is useless if you can't build it. That brings us to field and installation design. These documents are for the construction team on site. We create instrument location layouts, which are plan drawings showing exactly where every junction box and transmitter is physically located. We also provide hookup drawings. These are standardized details showing exactly how to pipe and wire each instrument type. To connect the field to the control room, we issue cable tray layouts showing the main routes through the plant. Finally, for the technicians connecting the wires, we provide junction box termination diagrams and interconnection diagrams, ensuring every wire lands on the correct terminal block. Engineering requires precision, and that is covered in the Instrument and Equipment Specifics section. The most voluminous deliverables here are the instrument datasheets. There is a unique datasheet for every tag, detailing process data, materials, and specifications. But we don't just pick numbers out of the air. We support these selections with calculations. We perform control valve sizing to determine CV and flow characteristics. We perform flow element sizing for orifice plates and venturis, and thermowell sizing to check wake frequencies against ASME standards. All of this feeds into the material takeoff, MTO, or bill of materials, which is a comprehensive list of all bulk materials like tubing, fittings, and glands required for construction. In high-hazard industries, safety is paramount. This is covered under Functional Safety and Specialized Systems. The governing document here is the Safety Requirements Specification, SRS. This details all safety functions and safety integrity levels per IEC 61511. We verify these designs using SIL verification reports and calculations like LOPA or fault tree analysis. We also utilize F&G detector layout drawings to justify detector placement, often using 3D mapping techniques. Beyond safety, this section covers specialized systems like the Analyzer System Specification for gas chromatographs, condition monitoring systems for rotating equipment, and communications systems like PAGA and CCTV specifications. Once the design is on paper, we have to buy the equipment. This is the procurement and vendor package phase. It starts with the material requisition, MR. This is the formal package sent to vendors to request bids for instruments or valves. Once bids are received, engineers perform a technical bid evaluation, TBE, to compare the vendor offers against the technical requirements. For large equipment like compressors, we create a package interface document. This defines the complete interface, including PNIDs, I/O lists, and communication protocols. These documents ensure a seamless integration of major third-party packages into the overall control system. The work doesn't stop once the purchase order is issued. We then move to managing vendor deliverables. These are documents expected from vendors after purchase, tracked via a vendor document register. For general items, this includes installation, operation, and maintenance, IOM manuals, and spare parts lists. For field instruments, we need dimension drawings and calibration certificates. For the control systems, the vendor must submit the approved system architecture, cabinet wiring diagrams, and the critical FAT procedure and report. Similarly, for major packages, we review their PNIDs and interface documents to ensure they match our design. Reviewing these is critical to ensure what arrives on site actually works. To summarize, a successful instrumentation and control project relies on a structured flow of information. We started with the conceptual design to check feasibility, moved to feed to set the rules and basis, and executed the detailed design to define every wire, tag, and safety function. Finally, we managed the procurement and vendor data to bring that design to life. By following this master document deliverable list, you ensure a well-structured process and a successful project delivery. Thank you for watching. If you found this breakdown helpful, please like and subscribe for more deep dives into engineering documentation and project execution.